Okay, so here we are. We get to now learn how we name organic molecules, at least for alkanes and alkynes. Alright, so the way this goes is all in terms of how much carbon you have present in your molecule. So if the most carbon you have in your molecule is only a count of 1, you are going to have a way of calling this molecule, and you use the prefix meth, not to be confused with other things, but this is how we're going to kind of depict the idea that you only have one carbon in your organic molecule. If you have 2 carbons, the prefix you use is eth. If you have 3 carbons, the prefix you use is prop. And if you have 4 carbons, the prefix you use is but. And all 4 of these particular prefixes are very different from any other prefixes you've used in the past. But the good news is that from here on out, if you go to higher counts, you simply use the same prefixes you've used for polygons in the past. So 5 is pent, 6 is hex, 7 is hept. And you could go all the way up to 10, in which case you have oct, non, and dec. And if we go as high as 11 and 12, then you have your undec and dodec. From 5 on, you basically use the same prefixes that you use for polygons. But the first 4, this is the new stuff: meth, eth, prop, and but. For 1 carbon, 2 carbons, 3 carbons, or 4 carbons. Alright, now what happens then is that you now take account of what kind of molecule you're looking at. Based on the type of molecule you have, the suffix is going to basically change. If you have an alkane molecule, then quite literally the suffix is ane, right? That comes directly from alkane. So if you only have 1 carbon and this is, an alkane molecule, the name is methane. If you have 3 carbons and this is an alkane, the name is propane. 7 carbons, alkane, heptane, and so on and so forth. If on the other hand you have an alkene, then instead of ending the molecule with the suffix ane, now you end it with the suffix "ene". And one thing that needs to be said is that for you to have an alkene, you have to have a carbon-carbon double bond. So never say methane, because that means that you only have 1 carbon, right? And you can't really have a double bond if there's only 1 carbon present. So this applies to carbons 2 and beyond. That's where you have your alkene. So ethene, propene, butene, pentene, hexene, and so on and so forth. If you have an alkyne molecule, meaning that you have a triple bond, once again, you need to have 2 carbons for this to happen. So you will start with a carbon count of 2, right? So you don't have methine. But you do have ethine, you do have propyne, butane, pentine, hexine, etc., etc. And the other thing we're going to look into is these branched components, which we're going to refer to as substituents. And if the name, substituent is not actually part of the longest linear chain, we're going to end it with the suffix il, right? So methyl, ethyl, propyl, butyl, pentyl, hexyl. You'll see a little bit later how the substituents get accounted for. But let's start first with the linear chains, or maybe cyclic. Okay, so we have this linear chain. We count the number of carbons. We have 1, 2, 3, 4, 5 carbons. So that means that we're dealing with a count of 5. And you have no double bonds, no triple bonds, so this is an alkane. And no oxygens, right? So this is definitely an alkane. 5 carbons in alkane means that this molecule is known as pentane. Okay, next. We have a 6-member ring, but this ring has a double bond, so automatically this belongs to the alkene family. It has 6 carbons, so you might want to call it hexene, but because the structure is cyclic, it's not hexene, but rather cyclohexene. So now you use the word cyclo, as your initial prefix, right? Hex to tell you that you have 6 carbons in the ring, and ene to tell you that there is an alkene present. Alright, then you have this other molecule, linear, but you have a double bond. So this is still an alkene. And you have 3 carbons, so this will be known as propene. All right, the last example, a little bit more esoteric. We have a triple bond, so this will be known as an alkyne. And if we count the number of carbons, here I'm going to label it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You have 11 carbons, so you're talking about undec as the prefix. So altogether, this is called as undecyne. All right, so this kind of gives you an idea. Now, the extra thing that probably I should say at this point is that the triple bond need not be at the end in this molecule. It could start at carbon 2 and go to carbon 3, or it could be carbon 5 and go to 6, or 6 to 7. In those cases, and even in this case, you need to specify where the triple bond starts to begin with. This one starts at position 1, so technically you should have to put a 1 hyphen undecene to give the proper name for this. I'm going to get to that a little bit later in the lecture. Okay, so let's talk about substituents. As I was mentioning, if you do have something sticking out from the middle of the linear molecule, that's when you're dealing with substituents. And the substituent could contain 1 carbon, in which case you have methyl, or it could contain 2 carbons, in which case you have ethyl. You could have propyl, butyl, pentyl, so on and so forth. But in addition to that, you have all these other options. You could have a halogen sticking out from one of the carbons. That's a substituent, and the naming is just a tiny bit different from the way you've been accustomed to thinking of them in inorganic chemistry. Instead of calling this fluoride, chloride, bromide, or iodide, you actually drop the IDE and change it with an O. So these are now known as fluoro, chloro, bromo, iodo. And you could even have a benzene ring attached to your alkane serving as a substituent, in which case we refer to it as a phenyl group. If you have a benzene ring followed by a CH2, and it's through that CH2 that you connect to the linear alkane, then you have a benzol substituent. The additional one that I'm going to introduce here is the alkoxy substituent, which is pretty much an oxygen bound to your linear molecule, but in addition to that, you have some other carbon content arising from the other end of the oxygen. And depending on how big this could be methoxy, ethoxy, propoxy, butoxy, etc., etc. And yes, if you do have cyclic alkanes behaving as substituents because they're sticking out of the biggest chain, then you will call that cyclopropyl, cyclobutyl, cyclopentyl. Always ended with that YL suffix as long as you're dealing with the carbon as your substituent. All right, now one last thing that I need to show you before we start doing the examples. When you're dealing with a 4 or a count of 4 for your molecule, right? If you draw it as a linear molecule, you're dealing with butane. But there's another isomer of butane that you can draw. This is known as isobutane. Notice that I truncated the linear chain to 3 and then I stuck the 4th one in the middle. This is known as isobutane, meaning isomer of butane. If you use these particular molecules as substituents, meaning that you could attach them, there's 2 ways to make this happen, right? You could attach them either from the end for both of the counterparts, and the moment that happens, the moment this becomes a substituent to something else, this is no longer known as butane, this is now butyl, and this similarly is no longer known as isobutane, but now it's isobutyl, as long as you connect through the end. But you could also have the connection through the middle, and notice that we still have the 4 member linear chain here, 3 member linear chain with a carbon, sticking out the middle, but now I'm attaching from the middle as opposed to from the ends. All right, the names of these attachments, these substituents, are known as sec-butyl and tert-butyl. And the reason why is because sec stands for secondary, meaning that the carbon here is attached to 2 other carbons, hence the secondary term for the butyl. Over here, however, the carbon is attached to 1, 2, and 3 other carbons, so this is tertiary in terms of its substitution, so we call it tert-butyl to account for that. But you can see the shapes are a little bit different, but they all have a count of 4. It's just where you're attaching the substituent from and what original shape you're dealing with. So be aware of these shapes, kind of get used to looking at them, because I'm going to give you molecules that contain them and you're going to need to name them as such. The last thing to be said is that sec and tert, which I wrote in italics, they don't actually count for alphabetical purposes. ISO does count, but sec and tert do not. So you actually will start at the B of butyl to come up with the alphabetical order, which is one of the rules that I'll talk about in the next section. So don't count sec and tert for alphabetical purposes. And then lastly, if you look at the three-member chain, right? So propane, if you have the attachment through the end, or if you have the attachment through the middle, you have two different substituents. Attachment through the end, simply change propane to propyl. Attachment through the middle, this is known as isopropyl, as in the isomer of propyl. All right, now with all of this, we're in a good position to start looking at examples. So let me stop the video right here, and on the next video, we'll go through the examples together.